Hey guys, it's Professor Goodman. This week's homework, this upcoming week, for I think it's, what are we, I think it's week 12 now? Week 12 homework should be this stuff. Um, Two sections due, homework chapter 15-1, which is pretty huge, like there's a lot going on, and then also 15-2, which it doesn't really need to be its own kind of thing, because they 15-1 and 15-2 are pretty much similar. It's just 15-1 is quite a bit longer. There's almost 20 questions, and then there's about maybe 6 or 7 questions in 15-2. They all deal with hypothesis testing. This week we're talking about, there's a few overview hypothesis testing questions again. Um, Knowing when you can use something called a z-test. That's what we did last week. We were only doing z-tests for our those population mean problems and the proportion problems. This one focuses all on population mean. There's no more proportions for this. Um, and There are two different types of tests. There's a z-test and there's a t-test. So a z-test you can use if basically the central limit theorem applies, right? So if your central limit theorem applies, which means n is either greater than 30 or your population is approximately normally distributed, if you have one of those two guys working, then you might be able to use a z-test. Now, the other thing you have to have for a z-test, you have to know your population standard deviation. If you don't know this or this and that, you may not use a z-test. In fact, in statistics, z-tests are hardly ever used because the population standard deviation is pretty hard to figure out, so it's hard for us to use z-tests. A t-test then is what you would use if your population standard deviation is unknown, and usually on top of that your sample size is smaller than the 30. Sometimes you'll have a t-test with a sample size that's close to 30, maybe even above 30, but you don't know the population standard deviation, so then that kind of makes it a problem. Okay, so let's do some of these problems here. So a few of these are just concept questions, and then we have to get into finding our test statistic using the formulas that we talked about last week and you are doing in your homework. You did in your homework last week as well. So let's read one of these problems and see kind of what we're dealing with here. Hypothesis testing, they're all application problems, so these are real world problems that if you become good at hypothesis testing, you'd be able to do these kind of things in real life. So these are actual studies that have taken place. Some of them are made up for our course, but some of these are actual real studies. I mean, of course, the numbers change, but these were studies at one time. Anyway, let's read this. The bar graph below illustrates Consumer Price Index, or CPI, differences between the second quarter of 2015 and the second quarter of 2016. As reported by the United States Department of Agriculture, USDA, and the Bureau of Labor Statistics, BLS. So that's what they're saying. Consider the CPI decrease in beef and veal at 6.4%. A certain state Department of Agriculture believes that the CPI decrease of beef and veal in their state was less than 6.4%. They obtain a random sample of prices from these two periods of times from 100 grocery stores, okay, so our sample size is 100, across the state, and find that the CPI decrease for beef and veal was 6.1%. So assuming population standard deviation is known, okay, so since we know the population standard deviation, this means we're doing a z-test. What conditions are true in determining whether or not a z-test can be conducted for this scenario? Alright, so first things first, we know the population standard deviation, so that's good. But now we have to have either n is greater than 30 or in the problem it should say our population is approximately normally distributed. Okay, so I don't see anywhere where it says our population is approximately normally distributed, but we do see this. Look at our n. Our sample size is 100. So n is greater than 30. So we have n is greater than 30, and we know the population standard deviation, so we can use a z-test. So that's all we have to say here. Sample size is large enough to conduct a z-test because n is greater than or equal to 30. Okay? So that's all you have to do. So you hit yes. I think that doesn't say anything about the population standard deviation. So if it asks about if it included about population standard deviation, that would be correct too, but it doesn't say anything. Just the sample size is large enough is the only correct statement out of all of those. Okay, so here it's the same problem. I think maybe did the numbers change slightly, but now we're trying to figure out what are the null and the alternative hypotheses for this scenario. Okay, so same problem, read all through it, then the numbers change. It says that a certain, consider the CPI decrease in beef and veal at 6.1%. So we're saying the decrease of this, I don't know what beef and veal means, I guess some kind of food. Price changes for selected at-home food categories, so I guess they're looking at beef and veal. They say it's equal to, this decrease is equal to 6.1%. But then somebody else comes along, so let's say it's you, and they say, actually, I think that the CPI decrease is less than 6.1%. So the decrease isn't quite as large, right? So it's smaller. So now we identify our null and our alternative hypothesis. So our H sub 0, which is the null hypothesis, and H sub A, which is our alternative hypothesis. Okay? So we know 6.1% is our magic number, right? So it'd be 0.061 decimal. So for our null hypothesis, it's going to be equals, right? So it'd be this guy. So we have our H sub O, so our null hypothesis, and the mean decrease is 0.061. Now be careful that this is not a proportion problem. We're considering the mean decreases of beef and veal. So since we're considering a mean decrease, and even though it is in a percent, it's still a mean. So you're not going to be doing proportions. So this would be your null hypothesis, and our alternative hypothesis is a little easier to figure out. Certain State Department, they don't give us our alpha, and sometimes having alpha in a sentence can help you find it. But in this case, they aren't really giving us enough information for us to actually determine anything, like determine the end result. They don't even give us our alpha, so or our significance value. So here it just says we just have to kind of read through it and figure out where your alternative hypothesis lies. The null hypothesis is always equals, but then here, this sentence, a certain State Department of Agriculture believes the CPI decrease of beef and veal in their state was less. So less than 6.1%. So somebody says, hey, actually we think it's less than the equal 6.1%. So then that would be your alternate hypothesis right here. Your mu is less than that 0.061. Remember, these two numbers are always going to be the same, right? And your null and alternative hypothesis, the only thing that changes is this logic operator, right? So this one says the mean is equal to this. This one says the mean, nope, actually it's smaller than that. Okay? This problem is the same, right? Same thing. Identify your null and alternative hypotheses. So you should be able to do that now. Here we go. Okay, so let's look at this. So this is another one of those, make sure you can use a z-test problem. Okay, so let's see. They conduct random samples of prices from 6 restaurants and 6 grocery stores across the state between 2011 and 2015 and find there was an increase of 7.9%. Are the conditions met to conduct a z-test and determine the significance of the data? All right. So let's see what it says. The increase, the conduct random samples across increase. What the heck? Why is it? Shouldn't be yes, should it? So there's only sample of prices from 6 grocery stores and 6 restaurants and 6 grocery stores. So that would only be, that'd be less than 30, right? And they don't have anything about your population standard deviation. Just says the graph shows an 8.1 increase in food category, and they don't tell you the population standard deviation. So I'm thinking that you would not use a z-test. So let's check this out. Yeah, so see, if you wanted to use a z-test, you would have to have at least normal distribution in your population. That would have to be known, or your n is greater than 30. Well, in this case it's not, right? It's only 6 restaurants and 6 grocery stores. That's definitely not 30, right? So, and also our population standard deviation wasn't even known. So it would definitely not be a z-test. So knowing the difference between when you can do a z-test and a t-test is pretty important. Okay? So here we go. Now we actually can find something. Well, yeah, let's do this one. All right, so we're going to calculate the test statistic. Now remember, there's a formula for this in Excel. I mean, not in Excel. There's no built-in function in Excel, but on your test you will have this formula. So all you have to do is know how to use it. Let's do this problem. So here shows major consumer da 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 da. The graph shows a 9% increase in the housing category for the nation, and one state department of agriculture believes the increase in housing category should be more than 9%. Okay, so there we go. There are 2 hypotheses, right? So, and then of course the rest of the problem gives us our data from a sample. They conduct a random sample of 300 rental and real estate properties across the state between blah 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 blah, and there was an increase of 9.3%. So in our sample mean was 9.3%, and we have a sample of 300 people. Also, we know the population standard deviation. So right away we have a z-test, right? We have n is greater than 30, and we had population standard deviation is known. We didn't have our populations approximately normally distributed, but we don't need that if our sample size is large enough. All right, so let's identify our hypotheses. So first off, remember the null hypothesis is always going to be equals something. Now here I just say, note that mu is equal to my population mean, in case you look at mu and you're like, what the heck is mu? It's not a cow, it's the population mean, mu. In fact, you can kind of think of a joke. If you ask what a Greek cow says mu. So, in case you find that funny. So let's see. 9% is kind of our magic number. So mu is equal to 0.09. Okay, that's our null hypothesis. Now the alternate hypothesis, we have to think about what are we trying to test? Well, here they say one state Department of Agriculture believes the increase in housing category for their state was more than 9%, so greater than 9%. So 0.09. Okay, now remember how hypothesis testing works. You're trying to find a contradiction in your null hypothesis, because if you find a contradiction in your null hypothesis, it makes your alternate hypothesis true. Okay, so if you can't find that contradiction, it means that you did not get significant evidence to overturn the null hypothesis. So here, we don't know exactly what the population mean is, right? I mean, we have an idea. They tell us that this graph shows a 9% increase, so got a pretty good idea that this is mu. But can we apply mu to all of the samples? Well, we're going to check that out here. So here they say that one state department believes the housing category for their state was more than 9%. So their state is different from the entire population. Okay, but here we don't know what our population mean is for that state, right? We only know a sample of the state. So mu, since we assume that the null hypothesis is true, you have your approximate value for mu, or you have what mu is. Now remember, in hypothesis testing, we're trying to show that this is not the case for mu, right? Okay, so now let's just fill in the rest of this stuff. So our sample size was 300. So we have 300. It should be, not bad, it should be down here. Oops. Okay, 300 should be here. My sample mean is the 9.3%, right? So 0.093. Okay, my standard deviation was, I think, 0.04. Oh, yeah, 0.04. Okay, now I can calculate my test statistic. Now remember, the test statistic, later, like, some of the formulas for it can get pretty large, but it's pretty easy to remember. It's just a special z-score, right? So since we're doing a z-test, it's a z-score. So all you have to do, take your sample mean, subtract off your population mean, put that in its own set of parentheses because you want the subtraction to occur before this division right here. Okay, and divides. Now I need my sample standard deviation. So click on your population standard deviation and divide by the square root of your sample size. Right, that formula should be pretty much common knowledge to us now. And there's your test statistic right here. So you'd hit copy, and you paste it over here, and you see it's correct. Okay? So you should be able to do this problem here. Same thing. Should be able to do this problem as well. It's also the same thing. They're really trying to beat... actually, no, this is a p-value problem, so we'll do that one. But this one's the same thing. They're really trying to get you guys good at this hypothesis testing idea, which I think is really good. Okay? So assume the population... So let's do this problem here. It's pretty much the exact same problem. We just have to change maybe the... we change the values for sure, but then we just have to find our p-value, and I'll show you how to do that, and then we'll go on to the next kind of problem. Okay, so here we go. They say fresh fruits, consider CPI increase in fresh fruits at 3.1%. So they already tell us what our null hypothesis is. It's 0.031, right? 3.1%. Okay? So now it says a certain state Department of Agriculture believes CPI increase of fresh fruits and their state was less than 3.1%. Okay, so this would mean we have less than our 0.031. Okay? Alright, so now we got to find all of our data. Now remember the mu, your population mean, you assume that the null hypothesis is correct. So we assume that it's true. So that means that right away our mu is 0.031. So right, just this statement here. Okay, that's why we say this. Alright, now our sample mean was found to be 3.0. So 0.03. Okay, our n, how large was our n? Well, our n was 300, so it's still 300. And what's our standard deviation? Our standard deviation is 0.01. So it's 0.01. Okay, there we go. And see right away, because I didn't delete my test statistic, and I have all this stuff typed out here, I only have to type out the equation for the test statistic once, and I get it automatically for free. But for the sake of repetition, let's go through this again. Okay, so I need my sample mean. So first type in equals. Okay, get your sample mean. So remember, you want to put the numerator here in parentheses, because we have a subtraction. Okay, minus this. Divide by your sample standard deviation. Okay, so that would just be your population standard deviation divided by the square root of your sample size. Alright, and there we go. So, just like we had before. This is our test statistic. Now, how do we find our p-value? Well, our p-value, remember, this is simple. The p-value is just find the probability, or the area, in with using your test statistic as the kind of dummy variable, in the direction of your tail test. So remember here, mu less than 0.031. This means that, hey, we're looking for, you know, how much smaller than 0.031 can we get before we're not considered 0.031 anymore. In other words, we're looking for values smaller than 0.031, and smaller, we know on a number line, means to the left. So this is a left tail test. Okay, so our p-value then is just going to be, this is our dummy variable. We want to find the probability around, and we have to find the area or the probability to the left because it is a left tail test. So our p-value is just going to be norm.s.dist. Okay, so our z, and it is always cumulative. And there you go. P-value is 0.041. So copy this guy over. Oops. Oh, I gotta go back and find it. So let's see. It should be. Crap, it's not that one. It is this one? Yes, it is. Okay. Hopefully. So let's see. It wants it to 4 places. So easiest way to do this is to make it 4 places in Excel. But I'm gonna not do that. So 1, 2, 3, 4. All right. So then it's just. Oops. 6. All the way down to 6. Okay. Hopefully I didn't mess anything up when I was converting that, but let's check. Okay, yeah, so there we go. So that is our p-value. Okay, now let's do a larger problem. Okay, so most of these you can see are kind of the same thing. They give you these charts, which I guess they're kind of useful to see, I guess, but I don't typically look at them. I just grab the values out, so you don't have to use them if you don't want to. I've been doing fine and I haven't been looking at them. Ah, here we go. Okay. Well, let's see. Let's do, instead of doing this problem, let's go down a little more and do another one. Ah, here we go. Let's do this guy, because this guy is actually, I think this guy's actually using a t-test. Yeah, so let's do this again. Yeah, t-test, I accidentally used norm.dist, and you can't use norm.dist in a t-test. So let's start fresh. Okay, so here we go. In 2010, Taco Bell had 5,675 locations across the U.S. with average annual sales of a lot of numbers that I don't really want to read, but starts with a 12 and ends with a couple zeros per store. So if anybody likes Taco Bell, I actually do like Taco Bell quite a bit. It is delicious. But anyway, assume the sales of a store vary normally. So with various locations opening and closing since 2010, remodeling and menu optimization, blah, 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 they do some quick analysis on Taco Bell's average annual sales to determine if it has increased. Suppose they take a random sample of the average annual sales over the last few years of one store from each of the various regions of the country shown in the table below. Oof. Okay, so in other words, we're only taking one store from each region, so not really a large sample, right? We're only looking at Northwest, Southwest, Midwest, Northeast, and Southeast. That's only 5 regions, so our sample size is only 5. So right away, we know we're not going to do a z-test because n is less than 30. But of course, if the population standard deviation is known, then maybe we could do it, but assume the sales of a store vary normally. They don't say that it's a. They don't say the population is standard the population is normally distributed. We only say assume the sales of a store vary normally. So we have that it might be normal, but we don't know for sure. So right away we cannot use a z-test. We got to use a t-test. All right, so let's answer some of these questions. So this is one store in the Northwest, one store in Southwest, one store in Midwest, one store in Northeast, one store in Southeast. Okay, so select the appropriate null and alternative hypotheses for this scenario. All dollar values are in thousands, so this just means this 1284 would be 1284,000, right? So about like 1 million, 1.2 million. Okay. So let's find our null hypothesis. So here, assume store average sales. They want to do some quick analysis on Taco Bell's average annual sales to determine if it has increased. So if it has increased past this. So that actually gives us our alternative hypothesis, right? HA. We say HA. We say that the mean should be greater than that starting value. So greater than this 1284,000. Okay, but then of course in the null hypothesis it's always equal, so it'll be your mean is equal to this number. So those would be our hypotheses, right? Okay, so which form of hypothesis testing would best fit this scenario? So choose the best response. So a z-test, we already know z-test is not going to work because what happened? Well, we have too small of a sample size, and we don't know if our population is normally distributed. We only know that, you know, it probably is, but we can't assume that the entire population is normally distributed. And also, on top of that, we don't know the population standard deviation. So we have to do a t-test. So it's this guy we got to do. So then right away we say a t-test would be the best form of hypothesis testing because the average sales average sales variable varies normally. That's a ludicrous answer. Doesn't make any sense. So let's go with this one. A t-test would be the best form of hypothesis testing because the average sales variable varies normally and the population standard deviation is unknown. Yes, that makes sense, right? We don't know the population standard deviation. It's not given to us here. So we can't use a z-test, we got to use a t-test. Okay, so now we got to calculate the test statistic for this hypothesis test. So first things first, they don't give us our measures of center or our standard deviations, right? We gotta copy this over and do it ourselves. So let's just throw it down here. We say match destination formatting. Okay, there we go. So to find our mean, so this is the mean sales of those, our sample mean, right? So this is our sample mean. Let's just put this here, and then I can throw it up here. So this would just be the average of all of these, right? Because this is the sales in thousands per one store in a region. Okay. So there we go. That's the average. Now we need our sample standard deviation. Because we don't know our population standard deviation, so we got to find the sample standard deviation. So this is easy because we can just do this stdev.s. Okay. Now be careful that you don't highlight the mean because the mean is not part of the sample standard deviation when you're calculating it in Excel. Okay, so there we go. So here I'm just going to throw the sample mean up here. I'm going to do equals sample mean. And then here's my standard deviation. I'm just going to do equals sample standard deviation. And now everything's up here. And now remember, our sample size here is only 1, 2, 3, 4, 5. All right, so see, look, here, I have to change the mean as well, right? Because in our hypotheses, we have is greater than 1284 and then is equal to 1284. So let's change that up here too. This is equal to 1284. And this is 1284, but this should be greater than 1284, right? That's what we're trying to show. So that's what it said. Magazine's average sales have increased. So if the sales have increased, that means that the sales are much larger now, or at least a little bit larger. Okay, so now since we're doing a hypothesis test, we don't know exactly what the mu is for all the regions, right? We don't know exactly what that mean is, but thanks to our null hypothesis, we can assume that it's 1284. Okay, so there we go. So we assume that if the null hypothesis is true, we have 1284. All right, so then look at this. So this already I have at least my test statistic here. Because I calculated all this stuff, right? And this formula is still in there. But let's go ahead and do it again. So for a t-test, everything is the exact same. The only difference is you have your sample mean minus your population mean. So you have this guy, and then you divide him by, instead of your population standard deviation, it's your sample standard deviation divided by square root of sample size. So see, it looks pretty much the same, right? Just the only difference is the sample standard deviation goes here because we don't know our population standard deviation. Okay, so this would be, of course, for your t-test. So that's for t-tests. All right, so let's do this. So take your sample mean, right? So this guy. Subtract off your population mean that we assumed was true because we're assuming the null hypothesis is true. So we're assuming the population mean is this guy. Divide by our sample standard deviation here. Okay, now we divide by the square root of our sample size. And there we go. Our test statistic is 0.6375. So this right here, because we're doing a t-test, this isn't called a z-score, it's called a t-score. But a t-score and a z-score, they're pretty much the exact same thing. They're just slight. A t-score makes up for the fact you don't know your population standard deviation and you're using your sample standard deviation. So the values differ slightly, but they mean pretty much the same thing. This is still the number of standard deviations away you are from your mean or your measurement of center. All right, so p-value. Now now we're looking for values that are larger than this, so we're looking to the right. So this is a right tail test. So in other words, our p-value, we have to find the area to the right. So now we're used to using norm, right? Like norm.s.dist, norm.s.inverse. But in a t-score, you have to use t. So you use t.dist to find this probability. Okay, so you put in your test statistic, and then there's this new thing called a degree of freedom. So degree of freedom is simply your sample size minus 1. So just click on your n, subtract 1 from it, and there you go. That's your degrees of freedom. And it's always cumulative. Okay, now this is cool, but this, just like the other distribution, finds the area to the left. So Excel will always find the area to the left. So if I want the area to the right, I have to do 1 minus, right? So I'll do 1 minus t.dist. Click on my x again. Degrees of freedom is your n minus 1. Remember the minus 1 or else you get a different answer. It'll be close, but it won't be the same. And then 5. So that'd be 5 minus 1 and then 1. Alright, so there we go. That's my p-value. Okay, so here we go. Calculate test statistic to 5 places. So I'm just going to be lazy and do this. So let's go down to 5 places. So this is 1, 2, 3, 4, 5. Okay, so that's good. And then this guy, they want it 4 decimal places. So 1, 2, 3, 4. Okay, so copy these guys over. So this is my test statistic here. And then this is my p-value. And there you go. Alright, so let's see. Hopefully there aren't any issues that popped up. Okay, everything looks good. Alright, so that's how you do a t-test. It's the exact same process as a z-test. The only difference is you're going to have to use t.dist when you're finding the p-value, and also you're using your sample standard deviation instead of your population standard deviation. Alright, so let's see if there's any more. I think most of these are pretty simple. Average lifespan, researcher and change. Choose your sample. 5 American. Select the alternate hypotheses. Okay, so this is just another one. So they're looking at life expectancy using males and females. Doesn't matter. It's going to be the exact same as before, right? So this is a smaller sample. It's less than 30. So what are we going to do? Well, population irradiation is unknown and our sample is less than 30. Well, what does that mean? That means you will be doing a t-test for this one. So do that problem. Should be the exact same. Let's see. This is, I think there's one problem that looks kind of weird. I think it was problem 15. Yeah, because we're talking about life expectancies, but then all of a sudden in part 6, they talk about the Taco Bell problem again. I think that's an error. I'm pretty sure, unless Taco Bell has, if you eat too much Taco Bell, maybe your life expectancy is smaller. Maybe that's, maybe that's what they're talking about. But this shouldn't be here. Hopefully it won't be here by the time you see this video, because I've notified them the mistake. So this shouldn't be here, but if it is, don't worry. If you're like, what the heck, what do I do? Just answer something randomly, and but hopefully it won't be an issue when you start doing the homework. Okay? Anyway, let's keep going. So most of these problems, they're the exact same thing. So your t-tests and your z-tests. So the only thing that's different is maybe knowing what to say at the end, right? So here is the Taco Bell problem again. So we did this problem pretty much. I think the numbers changed slightly. So when you do this problem all the time, you go all the way through, and then you find out what your p-value is. You compare the p-value to your significance level. If our p-value is less than 5%, let's just pretend and say, because you should already know how to find a p-value. Now I want to show you this part. So let's pretend our p-value was, well, let's see. Let me see what our p-value is for this problem without actually having to calculate it. So p-value, it says the p-value is 0.0205. Okay, so that's smaller than our alpha of 0.05. So in other words, we know we're going to reject the null hypothesis. So since our p-value is less than 0.05, we can reject the null hypothesis and conclude the average sales for Taco Bell locations in the US is less than this amount. Okay, so this depends on our hypothesis. Well, what's our hypothesis in the question? What are we trying to do? They say that they believe the average sales have decreased, so Taco Bell isn't making as much money as it used to. So that means it's a left-tailed test, or it's decreasing. So this is, we conclude the average sales for Taco Bell locations in the US is less than this amount. So this would be my answer right here. Let's see. Yeah, that should be the only one. I don't think there's multiple ones. There should only be one answer. Yeah, because it's a hypothesis test. You should only come up to one analysis. Okay, so there we go. There's that. This guy isn't too bad, right? Just you have, this is just, in fact, actually, it just gives you everything, right? So your test statistic and your p-value should be pretty simple to calculate. But you know, for the sake of continuing this, I'll do this problem over again. All right, so let's kill this data here. So it's just kind of getting in our way. Okay, so let's figure out our hypotheses. So here in this problem, it says the null hypothesis mu is equal to mu naught. And then they say our alternate hypothesis is not equal to. Ooh, so we're doing a two-tailed test. So this is actually good. Okay, so this is saying mu is equal to mu naught, and they say down here mu naught is equal to 131.5. So this guy is 131.5. Okay, and then here it's a two-tailed test, so it's just is not equal to 131.5. So not equal to, this means it can be either it can be too small to not be considered 131.5, or it can be too large. So this is a two-tailed test. Okay, so there we go. So we know we're going to have a two-tailed test. All right, so here's our data. Let's see if we're going to use a z-test or a t-test. Here we have our mu naught, right? We have our x bar, and ooh, we have s. Now remember, S is not your population standard deviation. Population standard deviation is sigma. So we have our sample standard deviation. So this means that we are using a t-test. All right, so here we go. So our sample mean was 141.1. So 141.1. Okay, and then our n was 70. Okay, and then our standard deviation for the sample is 25.3. So 25.3. So we have to use a t-test, right? Whoa, that's kind of ridiculous. Oh, it's because it's still 1284. Now remember, our population mean, based on our null hypothesis, we assume the null hypothesis is true, so our population mean, we say, is 131.5. Okay, so because we already have the test statistic formula, that's it. So that's good. Okay, now this is kind of the tricky part. So for a two-tailed test, our p-value, you're going to have to multiply it by 2. But first off, to find the p-value can be kind of strange. So you're like, well, it's a two-tailed test, and you always say that when we're doing a hypothesis test, and you find your test statistic, and the p-value is always the area in the direction of your tail test. Well, what happens if it's a two-tailed test? If it's a two-tailed test, so if two-tailed test, find p-value in the direction of the closest tail. So whatever tail is closest. So here my test statistic is a positive z-score, which means it's closer to the right tail. So you have to find the area to the right. Now, after you find this area, multiply it by 2. Because if you are doing a two-tailed test, this means your p-value is going to have to be twice the value it would be normally. Okay, so then since we're finding the area to the right, we know we're going to do 1 minus, but we have to do 2 first. So 2 times, then do 1 minus. Now we're going to do our t dot dist, because remember we're doing this is a t test. Click on your test statistic. Your degree of freedom is n minus 1. Right, so it'd be your 69. And then cumulative, it is cumulative. And oops, I forgot to put one more parentheses there. One more set of parentheses, or just one more parenthesis. There we go, that's my p-value. Alright, so there we go. That should be the problem. So let's see, hopefully I didn't do something incorrect. I think I did everything good. So let's see, round to 4 places. So this is 1, 2, 3, 4. So this would be 7. Now our p-value should be right here. Okay, so 0.022. So let me just double check. Looks pretty good. Yeah, so check answer. And there you go. So that is how you do a hypothesis test with 2 tails. So that's the process. It's the same for norm too. So if you ever see it for norm, don't freak out. It's the exact same process. When you find your p-value, to find your p-value, it depends on your test statistic. If this were negative, like negative 3.1, you have to find the area to the closest tail. The closest tail would be the left tail, so you'd find the area to the left. But here, because we had a positive z-score, it's the area to the right. So our p-value is the area to the right, and you got to multiply that guy by 2. So that's how you would do this problem. Okay? Good. So now this problem's the same thing. So check that one out. You should be able to do it. It's not a two-tailed test though, so it should be easier. But let's look at a problem from 15.2. Because 15.2 is also hypothesis testing, but for some reason it seems pretty similar to what we've already been doing. So see, like, it's even almost the exact same problem, right? Taco Bell problem. This is asking for the conclusion now. Another Taco Bell problem. They just really like Taco Bell in this, I guess. Okay, and then these guys again. So this is actually all stuff you should be able to do, right? So I'm not gonna do. Well, I'll do one problem. I'll say let's just do this one since we didn't do this problem, and then I'll let you guys go. Okay, so gender and age. So first things first, copy this thing over. Now, if you're working in Safari, or maybe even Internet Explorer, I'm not sure exactly, but sometimes this guy doesn't want to work. So make sure that you, yikes, it's a lot of stuff, so I need to zoom out a bit. But yeah, make sure that you get this, copy this over correctly and use it in Chrome. Because Chrome typically has a better chance of copying it over correctly. Okay. So here, a researcher wants to know whether the life expectancy has changed from 2013 to the present year. She collects a random sample of 5 Americans who are males and 5 that are females, and who have passed on in the last few years. Oh, this is depressing. The data in the table below. Okay. So here are the life expectancies, or 10 males and females that basically died in this study. So let's Look at all the dead people. Okay, so first things first, let's calculate our sample mean, because we don't have our sample mean, we don't have our sample standard deviation. We have our sample size, and it's 10, right? 5 females and 5 males, so it's 10. Now my mean is just going to be average of all of these guys. This is B15 over 2B over 2K15. Okay, and then my standard deviation is going to be the same thing, so STD dot and then S. Okay, and then I do my B15 to, was it K? Yeah, K to K15. Okay, so there's my standard deviation and everything. My N is 10. Now my mean has changed, right? So we got to figure out what life expectancy are we dealing with. And in fact, actually, what's our null hypothesis and our alternate hypothesis? Well, first things first, remember the mu here for the null hypothesis, it's always equals. So here it says approximately 61.5 years. So that's the average life expectancy in 2013. So our mu is equal to 61.5. Okay, so 61.5. And then we say this researcher wants to know if the life expectancy has changed. So that one you're like, oh, well, is it a left-tailed test or a right-tailed test? And the answer is both, because it is a two-tailed test. Because what does it mean if we're just looking for a change? Well, we're wanting it to be anything but 61.5. So it could be greater than 61.5 or less than 61.5. So if the average life expectancy has changed, this means we're dealing with mu is not equal to, so the same, not equal to 61.5. So again, it's a two-tailed test. Okay, so we've got all our data here. So you can see here, definitely, this p-value is 200%, so we're definitely going to be redoing this one. Okay, so here's mu. So this is, we're assuming it's 61.5, right, based on our null hypothesis. Our sample mean we got was 72.86. That was our average from the sample we got. And then our N, we're looking at 10 people. Okay, and then our standard deviation for a sample was this, right? Because we weren't given our population standard deviation, and our N is smaller than 30. So we're not going to be doing a Z-test again. We're going to be doing a T-test. So let's find our test statistic. Well, we already have it calculated because so you can see where saving this stuff is really nice, because all I have to do is find the correct information, type it all in here, and then automatically I get my test statistic. The only thing really you have to change is your p-value and all of these guys, because your p-value is dependent on what type of tail test we're doing. If it's a two-tailed test to the left, it might be different, or if it's a two-tailed test to the right, it could be different. Okay, so here, our p-value, our test statistic is 2.08408. So it's a positive test statistic. So this means we're going to be finding the area in the closest tail. The closest tail would be to the right, right? So it's actually the same formula, so I shouldn't have erased it. But anyway, it's good to know. But because it's a two-tailed test, you have to multiply it by 2. So again, it's to the right, so you have to do the 1 minus, now it's not norm, it's t dot dist, right, because we're doing a t-test, so it's 2 times 1 minus t dot dist. Your test statistic, the degrees of freedom, is your n minus 1 cumulative. All right, and again, just like last time, I forgot that parenthesis, but I just said yes because it adds it for me. And there we go, that's my p-value. Okay, so then you would answer all these questions. So what was it again? This guy is not equal to, right? That's our alternate hypothesis. Our null hypothesis is mu is equal to. Don't do t, because that doesn't mean anything at all. In the test, we're not testing the test statistic itself. We're testing the mean, right? So we're looking at the means. Okay, so then what form of hypothesis testing would best fit the scenario? Well, we already said it's going to be a t-test, right? Because we don't know the population standard deviation, but we do have that we could expect normal values, like a normal distribution. So a t-test would be the best form of hypothesis testing because the life expectancy variable varies normally and the population standard deviation is unknown. So it'd be this guy right here. Okay.
because z-test, definitely not. Z-test you need, so this answer right here just is stupid because you can't say you have a z-test and not know the standard deviation. So right away, anytime you see that, just throw that answer out. It's never going to be an answer. All right, so let's calculate the test statistic for this hypothesis test. So we already did that. Round to 5 places. Okay, so we're back to our 5-place guy. All right, so that's just this one. Throw them in here. And then our p-value that we already calculated was this guy. So let us throw him in here. Okay. And make sure it's correct because our last guy, yep, depends on that. All right. So what conclusions can be drawn based on the p-value? So here we're assuming a significance level of 5%. Okay, so for some reason they don't like to give alpha in the problem. Don't know why. Because usually that's how you can tell when like what your alternate hypothesis is going to be. But I guess these people are being a little more tricky. Okay, so here's our significance level, 5%. So we just have to see, is our p-value less than 5%? Is it? Well, our p-value is 6.6% or 6.7%. So that is larger than 5%. So this means what? Well, this means we cannot reject the null hypothesis, right? We don't have enough evidence to do that. So it would be something more along the lines of this. Let's read the whole question to make sure it's correct. So since the p-value is greater than 0.05, so that's correct. This one says less than 0.05, so kill that answer right away. The p-value is greater than 0.05. Our results are not statistically significant. Okay, I agree with that. And therefore, we must accept the null hypothesis and conclude that the average life expectancy for Americans is 61.5. Okay. That seems like the best answer right now. So let's keep looking. Since the p-value is greater, we can reject. We cannot do this, right? Since the p-value is greater than 0.05, our results are not statistically significant, and therefore we cannot reject the null hypothesis, and we cannot conclude the average life expectancy for Americans is not. This one makes more sense to me. The reason is because when you're doing a hypothesis test, you're assuming that the null hypothesis is true. So if you're assuming it's true, if you can't find a contradiction, it doesn't prove that it's true, right? That'd be like me saying, I think that the sum of two numbers is always going to give me a number, right? And then instead of actually proving it, I just say, here, my two numbers are 2 and 1. If I sum them together, I get 3, which is a number. Therefore, it's proved. We're saying, hey, this already works, and here is an example of this working, right? So it definitely would not prove that this life expectancy is 61.5. It might just mean that our sample was not good enough. So this answer is better. The p-value is greater than 0.05. Our results are not statistically significant, and therefore we cannot reject the null hypothesis, right? We cannot reject our H sub O. And then we cannot conclude our hypothesis was correct. So we cannot conclude the average life expectancy for Americans is not 61.5. I know it's kind of weird because it's like we cannot reject, cannot conclude, and not. So there's like a million nots in that. So that was kind of weird, but that's how you would do it. So be careful because two of these answers seem like they could be true, but then it comes down to if your null hypothesis ends up winning out, right? That doesn't mean it's true. It just means that your hypothesis was false. Okay, so that's all of this stuff. All the rest of these you should be able to do. But that's all of this homework. So if you guys have any questions, I hope that this helps you guys out quite a bit. If you have any questions, just let me know. But other than that, have a nice week.